Welcome back to the lecture. The earlier lecture talked about, in the earlier lecture I talked about the particle in a one dimensional box, and in the current one let us discuss the particle in a two dimensional model or 2 degrees of freedom model. The particle's position coordinates are given by two x and y, two coordinates in a plane orthogonal to each other, and then we discuss the quantum problem. The barriers are infinite. Therefore, if you remember the problem, p squared by 2m plus v, which is the energy term, gets changed to, or it is rewritten as p x squared by 2m plus p y squared by 2m, okay, plus v, and px is replaced in quantum mechanics by the minus h bar squared by the term minus h bar squared by 2m. The partial derivative now, because we have the wave function as a function of two coordinates x and y, and the momentum in the x direction is given by the partial derivative, and this is the square of the momentum. So, you have minus h bar square dou square by dou x square by 2m, and correspondingly for p y squared you have dou square by dou y square. Okay. This is the operator part for the kinetic energy of the Hamiltonian, plus, and the wave function is a function of x and y, plus v some potential times psi x comma y is equal to E psi x comma y. This is the two dimensional Schrodinger equation in which you have got the h, this term plus the v, h acting on the psi giving you E psi. And for the current problem of particle in a 2D box, we consider v to be infinite for all values of x other than from 0 to L, and all values of y from 0 to some other, say A or L1 or L2, it does not matter if it is a rectangular box. If it is a square box, then essentially you are looking at the let us see if we can have a square, something like that. So, 0 to L, and y is also 0 to L. Only in this region we are looking at the particle properties and the particle's behavior, and for all others we have v is infinity for all values of x less than 0 or equal to, and for all values of x greater than or equal to L, and likewise for y less than or equal to 0, y greater than or equal to L. So, this is the infinite boundaries that you have. It is not the single dimensional quantity, but it is a surface in a sense that we protect the particle from escaping this region, and inside v is 0, okay, between x and L, between y and L, and this is a square box. Okay. So, if we do that, obviously the differential equation simplifies without this term, and you have a derivative square in one direction, a derivative square in another direction, and then you have the psi of x y. Okay. Such a problem is easily solved by, is written in terms of a product of a function of x alone and a function of y alone. Okay. With this choice, it is possible to separate this equation minus h bar square by 2m dou square by dou x square plus dou square by dou y square psi of x comma y is equal to E times psi of x comma y into two equations, namely minus h bar square by 2m d square by dx square x is equal to E1 of x and minus h bar square by 2m d square by dy squared times y is equal to E2 times y, but these two constants E1 and E2 are constrained by E1 plus E2 is equal to E. Okay. The actual separation of this is given in the notes that accompanies this video lecture. Therefore, I would request you to look into that to see how this equation is separated into two one-dimensional equation, one for x and one for y, with the constraint that the energies for the two one-dimensional problems are related to the total energy as the sum E1 plus E2. Now, let us see the solutions. That quantity which I have written on the board is namely, this is the x equation and the corresponding y equation is that. Okay. Obviously, each one of them is like a one-dimensional particle in a box. Therefore, the solutions for each one of them will have a running quantum number for that particular equation. The x component of the wave function will be given by the solution. It's similar to the psi of x that we wrote, except that now we call it x of x, and now this will have a quantum number going from 1, 2, 3 to some value which we call as n1. In an exactly in an identical manner, the y equation will also have a free quantum number n2 which will run from 1 to 3 to whatever that we take. But please remember, these two quantum numbers are not independent in the sense they are connected to the total energy. The requirement that E1 plus E2 is equal to E. Now remember, the expression for E1 from the particle in a one-dimensional box, it is h square by 8m L square n1 square, a free quantum number in the sense it takes 1, 2, 3 integer values, and E2 is also given by h square by 8ml squared times n2 square, such that this equation is satisfied. Therefore, you have h square by 8ml square times n1 square plus n2 square is equal to the total E. So, this is the only constraint that comes out in the separation of the two-dimensional Schrodinger equation, that the total energy is the sum of the two one-dimensional energies, and that is possible because we do not have a potential which couples the two dimensions. We have put v is equal to 0, and therefore the method of separation of variables. Separation of variables. Okay. We have separated the x and y from the psi of xy. If you recall, the psi of xy, we have separated that into the x equation and the y equation. So, that process is called the separation of variables. Now, how do these functions look like? Obviously, you have the solutions for the quantum number n1 in terms of the one dimensional solution that you have seen in the previous lecture, root 2 by L sin n1 pi x by L, and the energy is given by n1 square, and likewise for the y with the n2 square, and with the constraint that the total energy E n1 plus E n2 is E n1 n2. You have seen that. Okay. What about the wave function? The wave function, now if you see this, the wave function psi of n1 n2, because it is obviously specified by the two quantum numbers n1 and n2, has the independent function x with the quantum number n1 and y with the quantum number n2. Okay. Each one is in an orthogonal direction. Okay. Therefore, you see this interesting thing, next line, when we have n1 is 1 and n2 is 1, when we have that case which is the starting point, what is called the lowest energy for the particle in a two dimensional box, you can see that the wave function is given by psi 1 1 x comma y, and is given by the product of the two functions that you saw, the x of x and y of y, which gives you sin pi x by L and sin pi y by L. Let me repeat this. When the quantum number is 1 1, the wave function is given by psi 1 1, and it is given by the product of 2 by L sin pi x by L and sin pi y by L, and the energy is of course the sum of 1 square plus 1 square times the whole thing. Therefore, the energy for this process E11 is h square by 8 ml square times 2. What is interesting is the next choice. You have psi n1 n2 as x of n1 y of n2. It is possible, if n1 is not equal to n2, it is possible to have the wave function given by x of n2 and y of n1, because the energy is simply proportional to n1 square plus n2 square times h square by, of course, 8 ml square, which is the proportionality constant. Therefore, you see that you have the same energy, but you have two physically different states, x of n1 y of n2 and x of n2 y of n1. Both states have the same energy. This is what is called a degenerate state. Degeneracy is 2, because there are two states which have the same energy but have different quantum states. This is the introduction for the particle in a 2D box, that the degeneracy is the additional factor. Now, how do these things look like? Let us simplify this picture. Now, I have a whole series of functions here with which you can fill up any number of pages if you wish. You see that n1 is 2, n2 equal to 1 corresponds to the wave function psi 2 1 with sin 2 pi x sin pi y by L, and n1 1, n2 2 gives you the other function, namely sin pi x by L sin 2 pi by y by L, and the energies are the same. So, if the quantum numbers are identical, there is no degeneracy, but if the quantum numbers are different for a square box, because we have chosen the length L to be the same, the square box gives you the solution that you have a minimum degeneracy of 2 if n1 is not the same as n2. And you can see that for 3 and 2 that you have here, the wave function sin 3 pi x by L and sin 2 pi y by L, and then 2 and 3, which is sin 2 pi x by L sin 3 pi y by L. So, the axis choice, the quantum number choice for a given axis determines the function's state. How do these things look like if we plot them? I mean, this plot looks fancy, but actually does not have much interpretation or meaning, but it is worth seeing the product wave function in 2 dimensions. Okay. So, you see the wave function, you see the wave function psi 1 1 using this picture. It is a half wave similar to what you had in your particle in a one dimensional box in the x direction, and it is also a half wave in the y direction, as you can see through the projection in the x direction here of this graph, and on the y direction also you have the same thing. Identical. Okay. What about the sine squared? The psi square, which is associated with the probability that the particle be found not in a small length region dx, but in a small area dx dy. Please remember psi xy, if you do that psi squared, dx dy is the probability that the particle will be in the small rectangular region between x and x plus dx and y plus dy. That is a small region, and you can see that the psi square is given like this. Therefore, you can create, you can visualize what would be the probability exactly the same way that you have visualized the particle in a one dimensional box, except that now we have a motion on the plane. And now what is interesting is when you go to different quantum numbers where there is degeneracy, psi 1 2, if you look at this, psi 1 2 is quantum number 1 for the x direction and quantum number 2 for the y direction. This is the quantum number for the x direction, and you can see that it is a half wave which is either up or down. It is either positive or negative. The reason being the y direction wave is a full wave. So, in this direction what you have is, if I may draw this, the wave function looks like that. In this direction the wave function looks like that. Therefore, when you take the product of these two functions, the negative side makes this wave function negative for half the length, and therefore you see that for half the length you have either a positive wave function or you have a negative wave function. That is only for the wave function. We know that the wave function is not that important, it is the square of the wave function which is important for probability interpretation, and you can see that psi square, which removes this negative character of the function, gives you now very beautifully the two n equal to 1 case for the x axis and the n equal to 2, if you remember the graph that you had for n equal to 2 for the y axis, and this is the x axis. Therefore, the features are captured, the wave function features are captured when you do a surface plot, and you can see that the pictures can be created for a large number of them, but there is a limit, 2 dimensions, and in 3 dimension we probably can use color at the most to distinguish the function from the 3 axes, but that is it, you cannot visualize this for n dimensions. So, let us conclude this part of the particle in a 2 dimensional box with some examples of the wave functions and the squares of the wave function for different quantum numbers. So, here is a 2 1 as opposed to 1 2, and you see all that happens is that for a 2 1 the wave function along the x axis is like this, and the wave function along the y axis it is like that. Okay. And you can see that actually, sorry, this is in the wrong direction, so let me erase that, because your 0 starts from here, therefore you have that, and this is the y axis. That is the reason why part of it is negative and the other part is positive. And the square of the wave function, you can see that there are two humps along the x-axis and along the y-axis. It is a quantum number 1, so you have only 1, similar to the one-dimensional y-axis. And let us see one or two more examples, and let me stop with that. This is the exercise here. What does this picture represent? There is 1 here along the x-axis, and there are 3 peaks. Therefore, you have, this is a y is 3 and x is 1. So, it is psi 1 3 square xy. So, the lecture notes give you many more such pictures, but in the next part of this lecture we will see what do all these things mean in terms of probability calculations and in terms of a new idea called the expectation values. We will stop here for this particular part of the lecture. Thank you.